Okay, let me start. First of all, I'd like to thank the organizers for giving me this opportunity. And it's very nice to be here. And so let me, okay. Today, I'm going to talk about the description of M5-branes in matrix models. And this talk is based on these two papers. And let me introduce my collaborators. So Yuma Asano was the previous speaker, and Shimasaki is in Keio University, and Terashima-san is in YITP. Okay, let's start. Okay. And so we had a very nice review in the previous two talks about this BFSS matrix model. So maybe I don't have a lot of things to say about this model, but the model we consider in this talk is the matrix models for M theory. So the typical model is the BFSS matrix model defined by this simple action. And this model was, as mentioned in the Danjo O'Connor's talk, this model was originally introduced as a regularized theory of a supermembrane. But if we try to understand this model as just the first quantization of a single brane, this theory turns out to be kind of pathological, and there is some kind of instability, and yeah, we cannot interpret this model maybe as just a theory of single membrane. And later, so some people, this is a very famous work by BFSS, but it is conjecture that this model is actually not just a regularized theory of a single membrane, but it gives the second quantization of M theory. And I think this is very interesting and a very strong statement. And let me explain how this is non-trivial and strong. So if this conjecture is true, so maybe one can first ask this question. So if this model is really the second quantization, does really this model contain all states in M theory? So for example, the fundamental object of M theory is the membrane, which is called M2-brane. So if this conjecture is true, the matrix model has to contain a single M2-brane state. And when it says second quantization, it has to also contain the multi-particle state. In this case, it corresponds to the multiple M2-brane state. And also, the M theory has another fundamental object, which is the M5-brane. So the matrix model has to contain also these single M5-branes and also multiple M5-brane states. And in the most general case, the theory has to contain multiple M2 M5-brane states. So these kind of complicated structure all has to be contained in that simple matrix integral. Right? It's very interesting and non-trivial. And this kind of question are kind of understood, relatively well understood for M2-branes, because we have some connection using some regularization or stuff. So we know some connection between matrix model and the states with M2-branes. But actually, if we include 5 branes, the story becomes very, very difficult. I will tell you why it's so difficult in the next page. But anyway, this has been a long-standing problem, how the M5-branes are described in the framework of a matrix model. So this is the main topic of my talk. Okay? And actually, we found a very nice evidence that M5-branes are indeed contained in the matrix model. Okay? And let me explain why M5-branes are so difficult. And first of all, the world volume theory of M5-branes is still unknown. And for D-branes, we know that it's described by the supermemory theory. So we can somehow connect matrix models to this low energy theory of D-branes. But for M5-branes, it's impossible. And also the second reason is, so supersymmetric matrix model has the supersymmetric algebra, of course. And looking at this structure of Suji algebra, we can find some central charges, which correspond to M2 or some D-brane charges. But in the Suji algebra of matrix models, this 5-brane charge is missing. So So this means even if we, if we had such well-defined charge, this gives us a clue to find the M5-brane configuration in matrix model, but we don't have, unfortunately. I don't know why, but it's kind of mystery. But so in summary, there is no guiding principle to find M5-branes in matrix model. So, and today, I will show that mass deformation of the BFSS matrix model, which is actually the BMN matrix model reviewed in the considered in the previous talks. And actually, this BMN matrix model is very useful to understand this problem. Okay. Okay. Before going to the detail, let me outline my work. So I just summarize my talk in the next this slide. So just concentrate just for this only this page. Yeah, everything is written here, and also next page. Just concentrate for 2 pages. Okay, and the BFSS matrix model was supposed to be M theory on 11-dimensional space-time, and by adding mass terms, we have a plane wave matrix model, and this corresponds to the M theory on the PV wave background. And actually, if we consider M theory on this curved background, actually we can see that there exists some spherical M2 and M5-branes, which have a 0 light cone energy. So there exists some special configuration of M2 and M5-branes. And according to the conjecture of the BFSS, this zero light cone energy states are mapped to the vacuum states of matrix model. So these objects with vanishing light cone energy should be described as a kind of vacuum state of the matrix model. Okay? So then this simplifies the problem a lot. Namely, so if we try to find this spherical M5-brane, then we can just look at the vacuum of the matrix model. Okay? We don't need to look at arbitrary states, but we can just look at the vacuum. Okay? So the target is very restricted. So the problem became very easy. But the story is not that easy, actually. The story is like this. So if you look at the classical vacuum configuration of the matrix model, you can see only M2-brane-like objects. So as reviewed in the previous talk, the vacuum is a fuzzy sphere. And we can see some kinds of M2-branes, but we don't see any objects like M5-brane. So then there is an interesting conjecture that this is actually written in the original BMN paper, but the claim is that the trivial vacuum, which means all matrices are 0 in this plane wave matrix model, correspond to the spherical M5. So I think this is very interesting because some trivial configuration corresponds to something very non-trivial, which is the spherical M5-brane in the curved background. Okay? So today we consider this conjecture, and so let me summarize our result. To check this conjecture, we apply the localization to the plane wave matrix model. So my work is not numerical, but analytical calculation. Okay, and we found that in some appropriate large and strong coupling limit, some moduli distribution of the SO6 scalar fields forms some spherical distribution. So this M5-brane emerges as a distribution of moduli of scalar fields. So like this. Okay? And we can also compute this radius of the distribution, and it turns out that it precisely agrees with the radius of M5 spherical M5-brane in M theory. So this is a very non-trivial matching. And we also generalize this result to multiple M5-branes, but maybe I will skip this case, and I will just concentrate on a single M5 case in this talk. Okay. Okay. Now I finish introduction, and in the second part, I will review the M theory on the plane wave background, and then I will explain the conjecture, and then I will show you our calculation and summary. Okay, let me review the M0 and the curved plane wave background. So this is the plane wave geometry in 11 dimension, and mu is the flux of this three-form gauge field. And when mu is 0, this just goes to the flat 11-dimensional space. Okay, and because of this mass deformation, the isometry is broken to SO3 to SO6, and I'm using the notation that I is 1 to 3, SO3 part, and A is 4 to 9, which is SO6 part. Okay, and let us consider classical M2 and M5-branes on this geometry. So for the moment, please just forget the matrix model, and let's just consider classical M2 and M5-brane living in this background. Okay, and let's start with the M2-brane defined by this Dirac-Nambu action. I think this I don't need explanation, so maybe you are familiar with these things. But starting from this action, we can take some nice coordinate or some gauge, fixed gauge. And then the theory, the Lagrangian or Hamiltonian, is simplified. And finally, we can derive this light cone Hamiltonian. Okay? And so here we have so this bracket is just a Poisson bracket on spatial world volume, and P plus is the light cone momentum, which is some conserved quantity. Okay, and so you see here, so all terms are positive squared, right? So if you try to find the zero energy state, you can just put each term to be 0. Okay, so it's very easy. And the non-trivial equation only comes from here. So if you put this to 0, it gives some non-trivial equation for xi. And so the vacuum configuration is given like this. And this equation is solved by a spherical configuration. And so this radius is also fixed by this equation to be this form. So here I took some unit, but anyway, radius is also fixed. So at the vacuum, we have a spherical M2-brane. And similarly, we can consider the M5-brane. So this is just a 6-dimensional, 1 plus 5-dimensional analog of the Nambu action. And starting from this action, we can again perform the same computation. And then we get the light cone Hamiltonian, which is similar to the M2 Hamiltonian, but it's a bit more complicated. But essentially, it's very similar. So all terms are squared and positive definite. And there is only one non-trivial term here, right? So here, this bracket with many arguments are defined like here. So it's just a naive generalization of the Poisson bracket. Okay, so if you try to find the vacuum configuration of this Hamiltonian, you just put each term to be 0 and solve. Non-trivial equation comes from here, so you have to solve this equation. This equals 0. And then you can find the solution is given by a spherical configuration. Here, the SO3 part is 0, but the SO6 part, its squared sum is constant. And this radius is also fixed by these equations, and it has some non-trivial power of the light cone momentum and also some numerical factor. Okay, so in summary, so if we consider M theory on the PVA background, there exists the spherical M2 M5-branes with vanishing light cone energy. Okay, and then let me go to the matrix model side. So how the spherical M5-brane is described in the matrix model. So here, the action of the matrix model is given by this. And we have a SO3 scalars and SO6 scalar. Okay. And let me again repeat the claim of the BFSS idea. So this model is conjecture to be the second quantization of M theory on the PV wave background. Okay? And it means that it must contain all states. In particular, the spherical M2 and M5-brane, which had a zero Lightcon energy, has to be realized as a vacuum states of this matrix model. Okay? So then let's look at the vacuum of this matrix model. So the structure is very similar to the M2-brane action. So the potential term has these four terms. And if you try to find a vacuum, you just put all terms to 0. And non-trivial equation comes from here, like this. And this is solved by the fuzzy sphere configuration. And any n-dimensional, so here n is the matrix size, but any n-dimensional representation of the SU2 generator solves this equation. Okay? The problem is that the fuzzy sphere is the regularization of 2 sphere, not of the 5 sphere. So this looks like M2-brane, but doesn't look like M5-brane, right? So we cannot see any spherical M5-brane object. So then this conjecture appeared, and trivial vacuum corresponds to the single spherical M5. This was written in the original paper by BMN. And later, this idea was generalized. So let me explain. It's a bit detailed, but let me explain. In general case, any representation gives the vacuum. So let's make an irreducible decomposition such that we have ns. So this small ns represents the dimension of each irreducible representation. Okay, so then the vacuum are labeled by the partition of n. So we can associate a Young diagram. So let's introduce Young diagram. So if we have a any one dimensional representation, we have a column with n length n1, and n2 representation, we have a column with length n2, and so on. Okay? And then let Ka be the length of S law. Okay? So this is just notation. Okay, then the claim is that when ns goes to infinity, actually this is a commutative limit of fuzzy sphere. So in this limit, some M2-brane is supposed to be realized. Now this is kind of well understood, but we can consider dual limit where the Ka goes to infinity. And this limit corresponds to the M5-branes. So if we take the limit where columns becomes very long, it corresponds to M2-brane. But if you had a very long row, then it corresponds to M5-brane. That's their clue. And for the trivial vacuum, these people check that this conjecture is very consistent with some mass spectrum of the matrix model. And okay. And but you can ask that. So okay, so this general case is a bit complicated. So let's just focus on the trivial vacuum case. Okay. In my talk, I will always assume this trivial vacuum. The trivial vacuum does not look like a spherical object, right? And because all matrices are 0. And for example, we cannot compute the 5-brane radius looking at this trivial configuration. So seemingly it's impossible. But actually, it is not the case. We need to recall that M theory is supposed to be realized in some limit where n goes to infinity and some p plus is fixed. And if you rewrite this limit in terms of the parameters in the matrix model, it turns out that this limit corresponds to a very strong coupling limit in the plane matrix model. So, in the strong coupling limit, even if the classical configuration is trivial, but still we will have some large quantum fluctuation. So the typical configuration of scalar fields will be very different from the trivial one. And this total configuration might be taking the same form as the spherical M5-brane. Okay? So that's the idea. And we check this idea by using the localization. Okay, so finally, I have 5 minutes, so let me explain our calculation. Okay, so let me. We need actually some assumptions, and one is the decoupling limit. So the system we consider is the M5-brane plus bulk gravity, but because we want to focus on this M5-brane, so we take the kind of decoupling limit of M5-branes, and in terms of the parameters of the Brane matrix model, this limit is given by the strong coupling limit in the Tofuto limit. So basically, we consider the Tofuto limit, where n goes to large and the Tofuto coupling is fixed. And then we take further limit where the Tofuto coupling also goes to infinity. Okay, so in this limit, the M5-brane decouples from the bulk. So I don't show you the derivation, but it's written in this page. And also, we made some assumption. We assume that in this strong coupling limit, the low energy moduli of the matrices are given by commuting matrices. Okay? So because we are expecting that some classical geometric objects appears from the matrix model. So non-commutativity has to vanish to describe some classical geometry. So we assume this property. Okay, let's do the localization. So here, from this action, we consider the theory around some specific vacuum of this form. And when N5 is 1, this is the trivial vacuum. And the localization is usually done in the Euclidean signature, and we also make the weak rotation. And because this Euclidean time direction is non-compact, we have to set some boundary conditions. But natural boundary condition is such that all fields go to the vacuum configuration at the infinities. Okay, this is just a setup. And then we consider a scalar field of this form. And then there exists supersymmetries such that it keeps phi invariant. Actually, there are 4 switches, so it is quarter BPS sector. And in particular, for example, if t equals 0, phi is just a complex combination of one of SO3 scalar and one of SO6 scalar. Okay? So the eigenvalue distribution of phi gives the modular distribution on this x3, x9 plane. Okay? And then the actually eigenvalue distribution of phi is computable by the localization. Okay? And then let me show you the result of localization. So any correlation function made of phi can be computable from the localization. And maybe I don't have time, so let me skip this, what is localization. So anyway, but it's a nice way to compute this observable in an exact way. And the saddle point configuration dominates, actually. So phi has this saddle point, and m is the constant moduli. Okay? So integration over this constant moduli remains. And the result is the following. So this correlator is given by this, and this on the left-hand side, right-hand side, we have this effective theory, which is defined by this kind of one matrix model like eigenvalue integral. Okay? And here, this constant, the small m is the eigenvalues of this constant moduli. So on the right-hand side, this expectation value is just a finite dimensional integral with respect to this small mi. Okay? So then, So then, using this effective theory, we can compute any operator made of phi. So it means that the resolvent is also computable by this effective theory. And because we assumed some commutativity of the moduli parameters, so eigenvalue distribution of this m can be actually identified with the distribution of the low energy moduli of x9, which was the imaginary part of this phi. Okay? And so evaluating, so evaluating this eigenvalue distribution of m, we can get some information about the distribution of moduli of this matrix. And we can evaluate So we can solve this effective theory, and actually it's solvable. And it turns out that this eigenvalue distribution of this M is given by some non-trivial function here. And this is also understood as the moduli distribution of X9. Okay? And now we got the distribution of a single scalar field, but now we have a SO6 symmetry, so we can consider some SO6 symmetric uplift of this distribution function. By the way, we have also real part here, but L3 is correspond to the moduli of SO3 scalar. But in this limit, this L3 is much smaller, so it's negligible, and only SO6 scalars expand. Okay, and then we got from this one-dimensional distribution, we can define an uplifted distribution function here. So because of the SO6 symmetry, we can assume that this uplifted function is a function of R, which is a distance from the origin in the six-dimensional space. And the definition is that the average of x9 to the nth power is equivalently computed by this uplifted function for any n. Okay, then we just substitute our finding here to this equation. And then we get the uplifted function is given by the delta function along the radial direction. So this means that SO6 scalars form a spherical shell in R6. And we can compute this radius also. And this radius is given by this. And this non-trivial power and also this numerical factor precisely agrees with the radius of M5-brane. So we conclude that in M5-brane limit, SO6 scalars form the spherical M5-brane. Okay, so the picture is the following. So at weak coupling, we had trivial configuration only, but at strong coupling, they form some non-trivial things. Okay, let me summarize. So we applied the localization, and we derived a spherical distribution for the low energy moduli of SO6 scalar fields in the M5-brane limit of plane wave matrix model. And the radius completely agrees with the radius of the spherical M5-brane. And actually, I didn't mention, but this result can be generalized to multiple concentric M5-branes, which correspond to the generic partition of the matrix model. And so this result means that multiple M5-brane states are also contained in the plane wave matrix model. So I think this is a very nice evidence for, yeah. And for the future work, I think we can also consider some excited states like rotating M5, or as I mentioned, the theory on multiple M5-branes is very mysterious. So it would be very nice if we can say something about this theory. And also, yeah, I'm discussing with Masanori and to do some numerical work on these kind of things. Okay, that's all. Thank you very much.
Thank you. Thank you very much. Thank you very much. Is there any question or comment? Actually, it's a very big question, but it's kind of question to you and also to David Bernstein. And somehow this story reminds me of a commuting matrix model you had 10, 15 years ago. You also observed the spherical S5. Is there any connection? It's also related to bubbling geometry.
Well, when I did my model, I just took the commutator squared and set it to 0. And then it was still possible to get an S5. And then just by looking at some Gaussian, I obtained something that looked like a delta function.
The model is very similar.
Well,
but you obtained that
I did it by hand, and it was an ansatz that I'm very surprised that it actually works.
I think our results show that his model appears as the kind of effective theory of this model. So
somehow maybe related.
Yeah.
Okay. Question, comment. Then one thing I wanted to ask is, so you assume that the moduli is commuting, and can you do any self-consistency check or anything?
Self-consistent.
Yeah, for example, if eigenvalue distribution become very huge, the off-diagonal element become heavy and negligible, that kind of, or numerical test is needed, maybe. If so, it's good for me.
Yeah, I think so. Yeah.
There is no question or comment, then let's thank Goro again.